Well, hello everyone, and welcome back to Adrian's Digital Basement. This is part 2 in the Apple II clone repair series. I recommend you watch part 1 if you haven't already seen that. There'll be a link in the description, because as usual, this is a continuation from part 1 where we left off, and in that part, we found some faults with this motherboard. The first was a dead video section that made the whole computer look totally dead, and that was caused by a bad transistor which had shorted, so I found that and replaced it. But then the computer still wasn't doing anything, and it turned out that there was a bad transistor in the reset circuit, keeping that from working as well. But not all was well after repairing the reset circuit, and it still wasn't working. And at the end of part 1, I figured out that there was a short circuit somewhere in the motherboard between a data line and an address line. And that kind of thing is going to keep a computer from working. Now, I want to preface this video by saying the runtime is very long, but it's worth it. It's gonna be worth it. This motherboard is very, very broken, and in my usual fashion, I like to try to figure out what's wrong before just replacing a whole bunch of parts, and that's what I'm gonna do in this video. So prepare yourself for a very deep dive and a very thorough and complicated roller coaster of a video where I have highs and lows and excitement and sadness and everything all wrapped into one. So without further ado, let's get right to it. Address line 3 is shorted to one of the data lines. Shorted to data line, looks like data line 2. Okay, so I am not seeing any shorts, by the way, not on the back of the board. I mean, this board's not in great shape, like it was sort of haphazardly assembled, but we definitely have that short, and all the ROMs are out, so it's not that. It's not the bus transceivers, because these are address only. This is the data line one, so it's not related. It's not going to be the CPU, it can't be, because it's on this side, away from the CPU side of the motherboard. So I need to look through the schematics, I guess, and just figure out what's on data line 2 and on the address line 3, because presumably there's some chip on here that's on both that's shorting those lines together. And it's like, it's a 0 ohm short, or there's a blob of solder or something on here. This is going to be a tough one to find. All right, well, I have been searching around in vain to find this, and so far, nothing. I think I have a lead though. I went around the entire motherboard and I looked for things that have both the data line and the address line that are shorted together, and really nothing has it except for the ROMs and the expansion slots. Now the 2 pins on the ROMs, well, they're not super close to each other, but on the expansion slots, they are pretty close to each other. On the expansion slots, basically just 1 pin away from each other and across. And the reason why I'm suspecting that it's the expansion slots, well, let's take a look at the GIMP scan here, and let's take a look at the routing of the particular pins that are problematic. So the pin that's shorted, the address line is 0, 1, 2, 3. It's this pin right here, and it's this data line right here. Notice how the traces are very, very close to each other. I'm thinking that when these expansion slots were installed, or, maybe this has been a fault from the very beginning, or I don't know, but it's too coincidental that these traces run basically right next to each other, well, right next to the exposed pins, and I think that that's the issue. And with a little bit of multimeter sleuthing, and I've turned off the beeper because I think that annoys a lot of people, I think I figured out that it's this slot right here where the short is happening. And the reason why I say that is because the resistance, which you can see there is 0.74 ohms or so, is the lowest on that slot. And here I moved over to the next slot. See, it's close, but it's higher. It's 0.77. And on this slot right here above, 0.80. Let's go back to the one I think is the one. Yeah, 0.75. So it's the lowest right there on this slot. So I think all I can do right now is try to desolder this from the board and visually inspect underneath. I sort of tried to look, under the slots and stuff. Maybe there's like a piece of metal under there, and I can't really see anything. But taking it off, I think, is the next course of action. So I'm going to break up the desoldering iron, and I'm going to try to remove that slot, and hopefully we'll find the culprit under there. All right, well, I got the connector off. Luckily, it wasn't too difficult. It didn't rip any traces. And well, unfortunately, when I took it off, there was still a short. Let me demonstrate here. 0, 1, 2, 3. Oh, what's this? No more short. Well, unfortunately, I wish I caught this on video, but I didn't. I was looking down here, and where I have the X-Acto blade right here, this is address line 3, and the trace for data line, the data line that's shorted, goes right by it, and there was just the ever so tiniest little extra piece of gold. This wasn't even a blob of solder, no. I actually just ran the knife one time like that next to the via, and the short is gone. Unfreaking believable. It was like a defect in the actual PCB itself. Okay, so I think we need to test the motherboard out. So I'm going to reinstall the ROMs. We're going to leave this slot out for now since that's not necessary for operation of the computer. We need to see if this thing is going to work. And I just realized that this IC I'd taken out for testing, and I think I put it back in one of these in the keyboard socket right here. Whoops. So I'm glad I noticed it before I turned on the computer. Let's pop that into there. Okay, now that's in the correct spot. Let's just do one more double check with the multimeter here. Let's just make sure it's on continuity. Sorry for the beeping. 0, 1, 2, 3, address line 3, and there's the data line. No short, everyone. And what I need to do as well is we got to bend back the lead on the bus transceiver because I can see it's still hanging out there. So we'll just gently push that back into position. So that goes back. It goes back in here. I don't understand. Like, this was a defect under the board. So how on earth was this thing ever working? I guess that's the question I have. And I'm really kicking myself for clearing that short. I couldn't even see there was a short. And I just took the X-Acto blade, and I just ran it, and then boom, short was gone. It's plugged into the retro tank. Oh, okay. Okay. We're definitely getting something. I mean, it doesn't look good. It's definitely problematic. But that looks a lot better than what we had. And we'll have to double check that the address line 3 looks good. Yeah, this is another fault. This thing has so many problems. So many problems. I'm really suspecting that the RAM might be bad. Because see how it's like shimmering and doing weird stuff there? That sort of screams bad RAM because that first bank of memory is absolutely needed. There's some letters at least. So it definitely is out of the graphics mode, so that's something. Alrighty, let's take a look at the address line 3. Look at that, everyone. It finally looks correct. And this is what the CPU is sending. And oops, let's get back on the right pin. There we go. That's what the bus transceiver is sending out. So this is no longer a short. And that's a good sign. So that means this computer is definitely one more step to working. Oh boy. A physical problem. This has never been off this board. There was no sign of rework. This was definitely installed at the factory. And it's definitely a manufacturing problem. And I'm assuming that it must have worked because, I mean, this thing, you know, had different RAM chips in it. So someone's done something with it. That would imply that this machine was running at some point. Okay, so now on to further troubleshooting. I think the next thing I'm going to do is I'm going to take out the RAM on bank 0. That's this first bank of memory here. I just don't know about this weird type of memory that's on this thing. And I'm going to swap these chips here with this bank up here because it's a different brand of RAM. So we'll just keep these in the same order that I took them out. And you know what? This is going to be a good test. While this is out of the board, let's see what it looks like on the monitor. All right, let's turn this on. Okay, so we're just getting a solid white screen now, which is expected because the RAM is what drives the screen output there. And, you know, we weren't getting anything, right? So because the first bank of RAM is absolutely necessary for the text mode to do anything. And just the fact that it was shimmery and stuff kind of makes me believe that it could be a RAM problem. Now, it doesn't seem like this machine is running any code, so I don't think it's necessarily a display problem. Although, you know what I should do? Let's hook up a speaker, because if we hear a beep when the system starts, then we know that, you know, it's actually running code. Now, I just noticed that the RAM I took out was all MOSTEC RAM, and the RAM I'm moving into that first bank is actually this weird RAM that I don't recognize the brand name of. I think what I want to do here is with this RAM in here, we just want to see if it looks different. Yeah, different, all right. It's just solid white. Well, that doesn't look good. Let's just power cycle this again. Well, that's, that's definitely worse. That is definitely worse, what we're seeing there. It was at least showing us letters before. I think what I'm going to do is I'm just going to take out all the RAM, and I'm going to put in known good tested memory. And since the RAM is all paralleled up, that means that any of these other chips that are misbehaving in these other sockets up here can affect that first bank. And you need the first bank to be working, because that's the 0 page, and the 6502 doesn't really work properly without 0 page. It's necessary for the stack and all that stuff. The ROM is not really gonna do much without any 0 page. I'm gonna grab some tested memory and we'll try it with that. Okay, I swapped out memory with some stuff I had. It's not tested. I can't find my bag of tested 4016. Let's see what happens now. Now, it's probably not necessarily a problem with the memory, and we can kind of test this by, let's take out this bus transceiver here for the data lines from the CPU. And it's still sort of shimmery and messed up. I put the transceiver back in. It pretty much looks the same there. Yeah, I wouldn't think it would do that if there wasn't a problem with the video circuitry, the part that's like reading it out. And actually the funny thing is it didn't seem to be this bad before when it was just showing that graphical mode. It wasn't this constant changing. Although now I think about it, it did have a little bit of shimmering, but it seems to kind of be worse off now than it was. Let's keep going here. Let's keep going with this problem. I think I need to clean up a little bit though, because it's getting really messy here down in the bench. Well, it's the next day, and I took a break last night after figuring out that underneath this slot here was a short, and even after clearing the short, the system wasn't booting, and I was messing around with the RAM, changing things around, thinking, still seemed like there was maybe a RAM problem. So today what I went ahead and did is I broke out the Retro Chip Tester Pro, and I tested all the memory that was on the motherboard, and I also went ahead and tested all the memory that I had taken out of my little bag of 416 RAM that I wasn't sure if it was good or not. And I'm glad I did that, because over here, this is all the memory that is good. These chips right here. These chips are all bad. Well, at least they test bad in the tester. There are 9 of the RAM chips that were on this motherboard. I think they were Siemens brand. And then 3 of the ones I'd taken out of my little bag were also bad. So I'm not exactly sure yesterday what I had put into this first bank, but I put in here all memory that is working. So all this TI memory and a couple of the MOSTEC chips. Incidentally, all of the MOSTEC chips that were on this motherboard, which were in this first bank, all test good, and it was the Siemens memory that are in these 2 banks that tested bad. A few of them did test okay, and they're up in this little pile here. What we have here now is all tested working RAM, all the ROMs are reinstalled, and I've gone ahead and I hooked up a speaker. With known good RAM in here, all the ROMs in here, and all the original chips in this motherboard, let's turn this on and see what happens. So, yes, the system actually has a beep. It sounds like the normal Apple II beep. Let's try that again. And look, it even says Apple II at the top. Now, it did also have a little bit of like, I don't know, static sound or whatever. So clearly there are faults on this machine. But the fact that it says Apple II there and we got a beep means that it's trying to work at least, right? It's actually trying to work. Now, power cycling the machine, see how it kind of weird? It was weird at first and then now it says Apple II. You get weird behavior. Now, there's no disk controller in this thing. It should just drop to the basic prompt. And, you know, we don't see a flashing cursor. We don't see the little, you know, bracket or, I don't know, square bracket that you get at the AppleSoft basic prompt. Now, over here on the keyboard connector, we can actually reboot the computer by grounding pin 3 to this pin. And it just causes it to do weird things. So that did 2 beeps, which sort of implies that it's crashed. Same thing there, and it's weird all the static that's going on, right? I'm just rebooting it right now. Nope, that didn't do anything that time. I mean, yeah, so we clearly have issues, right? Because we get this static and noise out of the speaker and stuff. But this is more life than we have ever seen out of this computer, ever. Now here's a card I want to try out in this computer. This is an Apple ROM card, and this one actually contains the original Apple II ROMs. So it's integer basic and the non-auto start ROM. So if I put this into a working computer into slot 0, what happens when you turn this on and the switch is in the up position, these ROMs will replace everything that's on the motherboard, and it should drop you to the machine language monitor prompt. To get to basic from the machine language monitor on the non-auto start ROMs for the Apple II, you hit Control B and enter, and then you will end up at integer basic. So let's pop this into the computer here, into slot 0, and I have it in the down position. And if we turn on the computer, and since it's in the down position, it's just using the onboard ROMs, and that's why it says Apple II. And if I reset the machine here, it's just doing exactly the same thing. Now, if we flip this switch and we reset the computer again, what's happening is it doesn't seem to crash as much. That's actually kind of normal. So with this card and the non-auto start ROM, when you actually put this in the computer, like an Apple II or II Plus or whatever, and you power it on, it doesn't even clear the screen. It just prints one blank line at the bottom with a little asterisk prompt, which shows you're a machine language monitor. If we power cycle the computer here, there's no Apple II banner at the top, and theoretically, it's waiting for us to hit a keyboard command. Now, I don't have a keyboard to plug into this, but it's just kind of interesting that we're not getting that kind of static or that crashing that's happening normally with AppleSoft Basic on the built-in ROMs. Just every single time, this is what you get. Oh, actually, this little pattern we see here reminds me of something. The transistor that's right here on the motherboard, I had it marked with a marker because it was one of those 1815s, like the video one and the reset circuit that had failed. And this is part of the color killer circuit. I actually went ahead and replaced this transistor just as a precautionary measure. I took it out of the board and I didn't even test the old one. I just put a new one in. Because the other two had failed, I just figured that it's a bad batch and this one was going to fail as well. It seems like this clone motherboard is a clone of not the Rev 7 Apple II motherboard, but like the earlier ones. And while it has a color killer circuit, which the original Rev 0 Apple II didn't have, it doesn't have the later, better color killer circuit. The later boards actually use some gates to disable the color burst entirely when the text mode signal is engaged. With this circuit, with this transistor, what happens is when you're in text mode, it uses this transistor and the resistor here to try to short the color burst signal to ground. So that's its way of disabling color, is to just short it to ground. It doesn't really turn it off, and obviously some leaks through, and the RetroTink and this monitor I have sitting on the bench right next to me both display color. And I happen to have an Apple II Plus that has one of the older versions of the motherboard, much more similar to the Apple II motherboard, and it has the same problem as this. So this might be actually a fun little project to do once I get this thing working, is to add those extra gates over like in this area over here, or maybe down here in the corner, with an extra TTL logic chip to disable that color burst, to kind of enhance the color killer, to make it more like the color killer on those later boards. Because personally, this is kind of an annoying problem, especially for me with this video capture. So now the question is, what's the next step here for diagnostics? The system is definitely trying to work, but it's crashing. And that really leads me to believe that there's some kind of problem with the RAM. And I know the RAM chips themselves are good, but I have a feeling the system is probably trying to write and read to the RAM. It's a sort of normal behavior when the system boots up, especially on a 6502. You need to have a working 0 page, and you need to have a working stack, which are all the addresses that start at hex 100. Otherwise, you're not really going to have a working system. And I have a feeling, because it's like printing the banner and it's beeping, I bet you that kind of happens really early on in the ROM code on the Apple II. And then when it goes to try to like initialize the rest of the system and get BASIC running, that's when it's just running into these problems and crashing. This definitely screams, oh, it's making random tick sounds right now, definitely screams that there's a problem with the RAM subsystem. Now, one of the issues with that is that the RAM subsystem on this is relatively complicated, just because of the way the main RAM, this first bank of memory here, is used for the display, video memory, high res, low res, all the different graphics modes, all the sharing of that RAM between the graphics subsystem and the CPU. The RAM actually runs at the equivalent of 2 megahertz, even though the CPU runs at 1 megahertz. There's just a lot going on the Apple II. So much so that after reading through the Apple circuit description about how the whole memory subsystem works, I was kind of stumped, to be honest. There are so many TTL chips involved and gates that kind of feed back into each other and shift registers, and I think I need a little bit of help. And by help, and the computer's just randomly ticking here, by help I mean a little bit of a diagnostic ROM. If you watched my TRS-80 Model 3 and then the Model 2 video, I used a Z80 diagnostic ROM that Frank, IZ8DWF, and my friend David Giller really wrote and allowed me to test out those systems. And it did it in a way that even if the memory wasn't working, we could actually have a functional diagnostic. Well, the Z80 processor is actually able to relocate the stack and doesn't really rely on the 0 page and has more registers and stuff than the 6502. So that is a lot more possible. But it is still possible to do some rudimentary tests of the memory subsystem from a ROM with some custom assembly code on the 6502 that doesn't rely on RAM or the 0 page or the stack. So I reached out to Frank, IZ8DWF, I've got a link in the description to his channel, and asked him, because he's a wizard, if he could whip up a little bit of a diagnostic ROM for this machine specifically to help me try to figure out what's going on. Now, Frank actually wrote the ROM that I used on an Apple II in a previous video where I tested out that first revision of the 6502 looking for that missing instruction. And in writing that ROM for the 2E, we had figured out how to like initialize the screen and write some text to the screen and stuff like that. So we already had like a little bit of a basics of how to boot an Apple II with a custom ROM. So what this new diagnostic ROM does is it simply initializes the text mode, and then it starts filling this screen buffer memory in the main memory on the motherboard with letters. And it just does like A, B, C, like the full screen, and it just cycles through all of the various letters. And at the end of each cycle, it also ticks the speaker, so I could hear if it's working or not. And the awesome thing about this code is very simple, is that it doesn't use the 0 page or the stack at all to run. So it could actually work with all of the memory removed from the system entirely. Well, the key thing to remember here, though, of course, is this first bank of memory is what is used to display the text on the Apple II. There's no dedicated video RAM like there is on a lot of other systems. So while I can take this RAM out and the diagnostic ROM will run, we're not going to see anything on the composite output because you need that memory at least working partially for anything to show up at all. The beauty of Frank's ROM here is that it only needs to shove values into RAM and doesn't rely on reading anything out of RAM to function at all. This is in contrast to the stock ROMs on this system, or pretty much anything you do on the system that requires you to be able to read from RAM properly for the system to not crash. Now, looking at this code here, it assembles into location FA00, and there's a specific reason for that. The system is off, by the way. This ROM right here, which is the top ROM in the address space, is sort of like the auto start ROM for this machine. In fact, you can take out all these other ROMs, and you really only need a ROM in F8, which is a 2K ROM, by the way, for the system to function. And that's because the 6502, when you first turn it on, it has a reset vector, which is up at the top of the address space, and it goes to that location to figure out where to start executing code from. It's basically a jump instruction that first runs when you turn on the system. So you need to have a ROM chip at the top of memory space, or the system is not going to work. Now, Frank's ROM specifically is a 2K ROM. It could fit right in this ROM socket, so there'd be no problem. One of the issues here, though, of course, these are 2716 EPROMs. They're kind of a pain to program because you need 25 volts. Not to mention, I only have a couple of them. So putting them in the system and then trying out this code and then erasing them and redoing that over and over again, a huge pain in the butt. What I can do, though, is use this card from Apple, because this thing uses 2316s, which are mask ROMs. It doesn't use these EPROMs, it uses these mask ROMs. And on my TRS-80 diagnostic ROM videos, I use this little adapter here, which I think is an adapter for 2332s, and it goes to a 2864. A 2864, of course, is an EEPROM, which means it's easily reprogrammable. I can just pop it out of here, reprogram it, put it back in, no erasing or anything like that. And a 2332, yeah, it's pin compatible with the 2316s that are on here. The only thing you have to worry about if you're going to use it that way is that depending on how the socket is wired up, you might have to load the ROM image, the 2K ROM image, up at address 800 hex in this chip for it to be visible to the motherboard. So let's pop out the stock ROM here. This is the F8 ROM on this Apple board, and let's plug in this little module. There it is in the board. And remember, switch up for using this card, switch down for the motherboard ROMs. So I went ahead and put Frank's assembled code into this ROM here, and I loaded it at 800. Let's pop this in the motherboard, and let's have this in the down position, and let's turn this thing on. Okay, so we're getting the normal beep we would expect. And let's turn this off, flip the switch to the up position, turn it on. There it is, it's running. So we're having a tick sound, let's hear this. Okay, we're getting color fringing because the color killer circuit, which I already talked about. But you can see here a couple things. It is cycling through letters and numbers and stuff. That implies that, well, the memory is working well enough that this ROM code is able to shove the values into the RAM, and then they are displayed by the video circuitry. So quite a bit of this motherboard is actually working. Also, take a look at this. We have lowercase characters. So this thing has a lowercase character generator on it. That's kind of a typical thing of a lot of clones, actually. But here's where we run into a problem. I have to caveat this that I have tested this ROM on another computer, on an Apple II Plus, because while we were developing it, we just need to make sure it worked and everything. And what happens right now, which we're seeing this solid white screen with a little bit of static on it, is on a real Apple II Plus. If I take this card and put it in another Apple II Plus, what you get right now are inverted letters. So it's going through all the same letters and numbers like it did, and they're inverted. And then it goes through a whole nother set of them that are flashing, and then it goes back to the regular letters and numbers. And this will do that in a second. There it is. Now we're back to, the normal at symbol and then ABC and whatever. I think it's starting at hex value 80. And on the Apple II, 80 is actually the first normal non-inverted characters. It's a little unusual to me the way the character generator works on the Apple II. It doesn't have like normal ASCII values in it for each of the letters. It actually has just 64 characters, and they're repeated 4 times. You have a normal set, you have a flashing set, and you have an inverted set, and then you have another normal set. And on this particular ROM, that second normal set has those lowercase characters on it to give this machine that lowercase capability. But there's a lot we can learn from this diagnostic ROM running on this motherboard. First things first is it's not crashing. It is completely working. I could let this run for hours and it would just loop over and over again with no crash. So the fact that the stock ROMs are crashing has got to be due to the RAM or access in and out of the memory, because that's the big difference between the diagnostic ROM that's on here and these ROMs. This doesn't use the RAM at all, and this does. So let's think about the symptoms of what we're seeing here with this diagnostic ROM. We're not getting the flashing, and we're not getting the inverted characters. Now, if we go to the circuit description book, this is a kind of a simplified diagram of how the flashing and the inverse works. It's actually quite a lot more complicated than this. So the character generator ROM here gets data line 0 through data line 5 from the RAM chips. That's what basically picks which character is going to be displayed. There's a data line 6, which, while it kind of passes through the character ROM, I don't think it really does anything in there. And it makes its way over to these gates here, which handle the flashing. And then data line 7 also makes its way here. And then it goes through a register through this gate, makes its way over here, all the way to that transistor, which we replaced, and then the composite video output. I think this representation oversimplifies the way this whole thing works, because you see the shift register here. This has parallel input. So this is the output from the character ROM, which is this chip right here on the motherboard, right? That's going to be a bunch of data bits that come out of that ROM chip, and they need to be converted from a parallel signal into a serial bit stream that allows it to follow the raster of the CRT, and that's the serial out right here. This diagram makes you think that it's simply like a bit coming from DL7 here that then just mixes with this gate here and then gives you inverted characters or flashing characters. But that's not actually the case. If we go to the actual diagram of the way this circuit works, it seems to be way more complicated than that. So I gotta preface this because I've done a lot of reading and a lot of sitting here trying to understand how this circuit works and the overall motherboard circuit as well. Here's the character generator ROM here. It's a 2316 on the original Apple II Plus. On this motherboard, it's a 2516, so it's an EEPROM, but that's either here nor there. So it has address lines that are the input to that chip, and then remember it has those outputs which are data bits, and that's the parallel signal that needs to be serialized through a shift register to be used as a bit stream to be displayed. The DL lines here, DL0 all the way to 5, and then here is 6 and 7. These are actually data bit lines that come from the memory itself. So these are the 4016 DRAM chips, the ones that we have on the motherboard that we know are good. There's a pin here on the chip that says DI, and that's a data input pin. And that's coming from the processor itself, well, the transceiver on the processor, the LS245 right here. This is the input to the RAM. So anytime the CPU is trying to store anything in the RAM, like for instance, those characters we were looking at with the diag ROM, that is coming through these lines into the input pins. One thing that's interesting about 4016 chips is that they also have a separate output pin, and that's right here, DO. And we follow it all the way over here. DO makes its way into these chips here, these 74LS174s, which basically connect that to these DL signals, 0 through 7. And remember, those are the lines that we were seeing over on that video section a moment ago. There's actually a really good block diagram a few pages up here in the documentation that it kind of explains what's going on with this DL versus the regular data lines. So here's the microprocessor, and we have that transceiver, and it makes its way up to the data bus. That's the D0 through D7. And if you go over here to this section, right there are the DRAM chips, and you see it's pointing into the DI side. And then the DO side, the output of the DRAM chips, goes down here to a latch, and then it goes over here to a data mux. So imagine when the CPU is trying to read from the DRAM, the DO signal, which turns into those DL signals, that needs to make its way back to the regular data bus D0 through D7. And this data mux here is what makes that possible. This data mux seems to switch between the DL signals, DL 0 through 7, and the keyboard data. So I guess whenever you're trying to read the keyboard, this mux switches over to that, and then it shuttles that data back onto the regular data bus where the CPU can use it. Otherwise, what's happening is the output data, the DL, which stands for latch data actually, comes down here and it makes its way into the video generator. Now the reason why it's set up like this is because on the Apple II, the video circuitry is constantly reading out of the memory. And I mentioned this earlier that the memory actually runs at 2 megahertz because the CPU is reading from the memory at 1 megahertz, and in the off time, in the other half of the clock cycle, is when the video circuitry can then read from the memory to display what's in the RAM on the screen. That's the key point. What is going on here is it's latching the output of the memory and allowing the video generator to read that signal and then display it on the composite video output. And to facilitate that constant refreshing of the RAM and that display of the RAM on the screen, there's this video address generator right here, which there's a whole circuit there, clocks driven or whatever. And that actually drives the sync generator, which creates the sync signals that goes to the composite. But that also goes through the memory mapper here, which allows the different like screen modes and stuff like that, or helps facilitate that. And then it goes into the DRAM through the address multiplexers so that the RAM is told by the video circuitry, hey, show me the screen memory, and then it outputs that down the data bus line here back into the screen. But then sometimes you notice there's a little switch right here, and that's because the CPU also needs to talk to the RAM sometimes and read a particular memory location. And when that needs to happen, well, this little switch goes bloop, and then the address bus right here, which is coming from the CPU and the bus transceivers there, is what tells the RAM what needs to be accessed. So that's the reason why it's using the data out and the data in separately, which is a little different than most systems I've ever worked on. The Commodore PET, for instance, uses the same type of memory as the same DRAM, but it just connects the DO and the DI line together, and it doesn't use the fact that those can be separate for anything. Anyhow, that brings us back to this diagram of the entire video circuit, because remember, what we're seeing when that diagnostic ROM is running is that instead of inverted characters and flashing characters, we're just getting that solid white screen with that kind of weird interference going on. So there are the data lines right there, and data line 7 is what goes into this gate right here, and I don't have it handy. Oh wait, maybe I do. Yep, there it is. This is the gate right here, data line 7, and that handles the flashing and the inverted characters. And data line 7, there it is. So this is part of that flashing inverted signal, but notice this actually goes up into this chip here, and it goes down here, and it goes into that, and it goes all over the place, and this chip right here actually feeds back up to here, up to the serial shift register, so there's like a feedback loop happening. So it's all rather complicated. But one thing we can be sure of is that if there's a problem specifically in the flashing and the inverse part of this motherboard, the thing should still display normal letters. We're just not going to see the flashing. We're not going to see the inverted characters if, for instance, data line 7 wasn't getting through to this circuit. In fact, here's something we need to consider about the way the Apple II character set works. Remember I said the diagnostic ROM begins at hex 80. That's this character right here, the @ symbol. And it runs through all of these and everything looks normal. And when it gets to the question mark, which is the last symbol, it switches all the way back to 0, 0, 0, 0, 0, all zeros, right? And that's this symbol right here, which should be just an inverted @ symbol. And we're getting nothing at all. And it makes its way through all of this, and then it gets back to here and it starts working again. Well, what is the only thing that differentiates this whole upper section and this whole lower section? It is the data bit 7. This chip right here on the motherboard is the data bit 7. That is the line that differentiates these two sections of memory. What we can ascertain by looking at the diagram is that when data bit 7 is high, which means it's these upper characters, everything is working normally. But when it's 0 or low, something is very wrong all of a sudden. So I have an idea. Let's remove a couple chips from the motherboard that allow the DL or the latch data bus lines to make their way back to the CPU. Specifically the data mux right here. Because the ROM code is not reading from the memory at all, ever, this is actually not necessary. And we don't have a keyboard connected either, right? So at no time does the CPU ever try to read from RAM, ever. So we should be able to take these chips out and have the system still run through that entire diagnostic ROM with no issue. And here we are, these are the two muxes. So right here, this is the keyboard connector. So these are the data lines that come from the keyboard. And then we have DL0 through DL7, right? So that's everything on the latch data bus line that's used for the output of the RAM that goes to the video circuitry. And this is what connects it here when the RAM select is turned on, or I guess some kind of keyboard signal, probably to read the keyboard, that connects these to the data bus lines that make their way over to the CPU. I really just want to test that if we remove these chips, we shouldn't see any difference at all. If the problem right now exists in the video circuitry entirely, then pulling these chips out should just do exactly the same thing. We should just see a count of all the letters and numbers, and then it should go to the inverted ones, and we just see that white screen with the interference, and that's it. So I'm going to pull out B6 and B7, which are these two chips right here. So let's just pop these out of the board. And with the switch up, let's turn the system on. I can hear it ticking, so it's definitely running. There we go. We're going to use the large one so everyone can see clearly. Okay, so far so good. This is as expected. We are just getting all the letters and numbers. Now, if I try to run the regular AppleSoft ROM, no way it's going to work at all. Those will absolutely try to read from memory, and well, that's just clearly not going to work with these chips out of the board here. But let's just see what happens. Okay, we're almost there because we're getting through the uppercase or the lowercase letters. It's about to switch over to the other one. And here we go. What's going to happen? Okay. This doesn't really make sense, right? What's going on here? Because these muxes have nothing to do with what's displayed on the screen at all. Remember, all they're doing is connecting the output of the data bus from the RAM chips to the CPU bus when the CPU is trying to read from the RAM. But the CPU is not trying to read from the RAM, so they are out of play entirely. So what this is telling us is that, oh, there we go, it's back to normal letters. So this is telling us that there's definitely something wrong in the RAM video part of the circuitry. And it's not these chips. I don't even need to test these because taking them out, it did change things a little bit, but frankly, they shouldn't have had any effect at all. And taking them out, we're still seeing that garbage. We're not seeing the normal letters that we should be seeing. And remember, if inverted and flashing is bad, we should still see the letters, but we're not. We're literally just getting random garbage. So what I'm going to do is we're going to pull out the data bit 7 pin here, or chip, RAM chip, out of the board here. So we're operating now with no bit 7. Now remember, that's going to have minimal effect because the only thing that this RAM chip is used for is to access those inverted characters and the flashing characters. So if everything is working perfectly with this chip out, when we get to past the lowercase letters, well, we should theoretically actually just see these letters repeated over again, because remember, it would just be flashing and inverted. Here we are, we're just about to change over. Okay, okay. That is fascinating. So this is telling us that there definitely is some kind of interaction that when this chip, this bit 7 chip, is in the motherboard, it's corrupting all of the signals. Like it's not just corrupting the data bit 7, like causing some inverted or not inverted or whatever. It's corrupting everything. And what's weird is that with the chip in there, the upper 127 characters, remember, starting from hex 80 all the way to FF, still display correctly. It's only when data bit 7 is set to 0 does it start corrupting everything. And I'm just going to pop these MUX chips back in. These are the ones that connect the output here to the CPU. And let's see if that changes anything at all. All right, here we go. We're about to roll over. Look at that. It's still working. This thing really only messes up when this chip is in the board. Now, you're probably thinking, oh, it's probably a bad chip, right? Let's just grab a random other chip here, and this is absolutely tested. I have a tick mark on all of these. It all went through the Retro Chip Tester Pro. Let's pop this in here. I bet you it's still gonna mess up because I'm pretty confident when the Retro Chip Tester Pro says a chip is good, it's pretty much always good. It has problems testing chips that are sort of marginal, that work in a TTL environment, but don't work on this CMOS device, Retro Chip Tester Pro CMOS, and that can cause some issues with like thresholds and stuff like that. So I can't necessarily rule out that all these chips here are bad, but this one that's good, I think it's definitely good. But let's just see what happens. MUXes are back in, and all the RAM chips are back in. And here we go, it's about to roll over. Okay, yep, exactly the same as before. And in fact, if we turn off the system, I flip the switch. There we go. Apple II, leftover letters from before, I guess. And it seems to be crashing. Let's just try again. Yeah, okay. Same exact behavior. I'm really excited about the fact that this diagnostic ROM exists, even though it's very simple. Because if I just take this RAM chip out of the board and we flip this down, we try to go to AppleSoft Basic, the system doesn't even work at all. Like there's no beep, there's no nothing. But if I turn it on the up switch, you know, we're getting the ticking because I know it's working. So just taking this RAM chip out results in a completely non-functional system normally. And I wouldn't have been able to see the fact that taking that chip out actually changes the way that that test pattern is working and allow me to definitively see that data bit 7 is the problem on this motherboard. Okay, so with the diagnostic running, if we go to the input pin on the 7th bit, there's stuff happening here. The problem is the data input line on all the RAM chips is shared across everything else on the motherboard, including all the ROM chips and well, any other peripherals. And we have to remember the ROM code is currently running right now and it's loading bytes and stuff out of the ROM, and sometimes there might be bit 7. So that doesn't imply that this is something that's being written specifically to RAM. The only way for us to see that is to look at like the RAS and CAS lines and kind of gate that stuff all together. But what we can look at is the output lines of the RAM, because remember, that's only what's being read by the video subsystem or the CPU if it were trying to read from RAM, and we know it's not currently. So here we are on the data output line of bit 7. And this doesn't really make sense to me, because currently the only thing that's reading from this chip is the video subsystem. Remember, it's not the CPU, because I can pull those MUX chips out and we were seeing the same behavior. So what is this exactly? Okay, so here we are on data bit 1. So I'm on the output pin of the second RAM chip that's like furthest away from me. And you can see there's like letters being displayed on the screen and there's all sorts of stuff happening here. And if we go to the next one over, so this is data bit 2, it looks exactly the same. And if we go over here to data bit, I don't know what this is, 5, same, right? This is it reading all those letters out of the screen memory and displaying them on the screen. Look what happens here when the screen goes white. I'm currently on, I don't know, data bit 4. Where did everything go? It's just gone. And now I'm on the output pin of data bit 6, and it similarly looks like nothing. If we power cycle the computer, there we go. We have the normal signal. And here we are back on the output of data bit 7, and it just doesn't make sense what we're looking at. It just doesn't look anything like all the other lines at all. So something's going on this motherboard, I think, with this line specifically. I think we can kind of test this. I'm going to pull this out of the board. And with this chip out of the board, what we need to do is we need to take a look at data line 7. And I can't really probe these types of sockets. They have a very small hole. And if you stick the oscilloscope probe in there, it actually damages the socket. So don't ever do that with these old type. But data line 7 is available here on B7 pin 6. So let's take a look at that pin. We are seeing a signal on there, but the RAM chip is not in the motherboard. It's impossible. Nothing else drives that signal except for the RAM chip. Nothing. So the only thing I can think of that's going on is there's either a short between some other signal and data line 7 or the latch 7, or there's a problem with one of these chips or something like that that is also connected to data line 7. Like it's feeding some other signal, like through an internal short on the chip, back into data line 7. So I think what I need to do is remove this B7 chip and then look around on the board and look at what else is also connected to data line 7 and see if I can remove those from the board. Okay, this is what I came up with. I took a pin off an old dead chip and I broke it off and I put the pin in the socket here and I clipped the multimeter, or I clipped the oscilloscope onto here. That should allow us to probe it. Yep, there it is. And we're not running the diagnostic ROM right now. Let's flip this up. And the diag ROM is not running. Why? Diagnostic ROM is running, but I'm not hearing the ticking anymore. That's weird. I'm not sure what I did. I just took out the one multiplexer, the one that connects the data latched lines to the CPU bus. Well, that shouldn't have any effect on the speaker. Let's put this back in. Nope. Okay, well, maybe I broke something else. Oh, the speaker came off. What the heck? Oh, okay, well, let's get a different speaker. I think I have this one right here. Let's see if this one works in place of that one. Yes, it does. Okay. I was like, what just happened here? Why is there no more ticking? Okay, this is what I just thought about. I'm going to use the second channel on the oscilloscope and another probe, and I'm just going to start probing around, like on the RAM chips, for instance, and I'm going to look for any other signals on them, like maybe the RAS or CAS lines or whatever. Maybe it's an address line that looks the same. And that might help us figure out where this signal is coming from. There we go. We're getting that stuff. I'm going to unplug the speaker so we don't have to listen to it. And I'm just going to start probing around. And first of all, let's start right there. So I'm on the actual same pin as the other probe. So we're seeing identical signal. So I'm going to look around and I want to try to find another identical signal. So I'm on the adjacent RAM chip here. I'm on pin 2, which is just, I don't know, something else. Pin 3. Hey, what is pin 3? Because there it is. It's exactly the same. And that is not right. Pin 4, nope, different. 5, different. 6 looks different. 7, totally different. Here on pin 10, I'm skipping the end pins because that's like the different voltages, like plus 12 and minus 5 or whatever. That one there, nope, different, different, different. That looks sort of similar, but definitely not the same. What pin is this? That's pin 14, and that is 15. Okay, so pin 3, and I'm on a different chip. That's it. We got to look up what that pin is, because clearly we have a short. We have a short. In fact, if I take the probe off there, let's turn the power off, and let's use the multimeter here. Okay, so I'm on pin 3 of the chip next door. Yep. 0.7 ohms. There's the short. The data output pin of the 7th RAM chip here is shorted to pin 3 on all of these RAM chips. And here we are on the pin out for the RAM chips. It's the right pin, and it's driven right here by this gate. That poor gate. It's been fighting the whole time with the output of that 7th RAM chip and its output to try to drive that right signal. This is probably the exact same problem as this slot connector. You gotta be kidding me. Just quickly want to insert a little voiceover while editing. You might be wondering why this worked some of the time, like when data bit 7 was high, we got normal characters, but when it was low, as in the first 128 characters, we were getting complete corruption of everything. The reason why that was happening is because TTL logic, which is what's used on this computer, has a very strong pull down, but a very weak pull up. What I mean by strong pull down is it can sink a lot of current through the transistors inside the chip when it's pulling down to ground, but
when it tries to pull up to 5 volts to output a high signal, it is very, very weak and can just barely pull the signal up to 5 volts. So when that RAM chip was outputting a high signal or 5 volt signal, that gate that drives the write signal that goes to the RAM had no trouble pulling it down to ground. Now, we weren't seeing any visual artifacts of it writing to memory, and I think that was very specifically because that write signal is happening in the off cycle from when the display is reading the RAM out and showing you what's in the contents of the RAM. This goes back to what I was talking about earlier, how the CPU and the display circuitry share the RAM with the RAM running at double speed versus the clock speed of the computer so that they don't interfere with each other. As soon as the RAM chip was trying to display the lower 128 characters, the flashing or inverted characters on the Apple II, it was outputting a low signal, it was pulling it down to ground. And that immediately overrode that gate that was toggling the write signal on and off, and that was essentially making all of the RAM writable all the time, or any of the time that bit 7 was pulled down, which immediately corrupted the contents of all the memory. So I hope this additional explanation makes it a little more clear about what was going on with this particular short.
So let's go to GIMP. Let's take a look here. Let's find that RAM chip. So there it is. This pin right here, that's the output, the data out line on that 7th RAM chip. And look at that trace right there. So pin 3, which we know is shorted to that pin, it goes right by there. It's got to be right there. Like, I don't see any other way this could be shorted anywhere else because, you know, this trace is over here. It's not going to be shorting to the outline over here. It has to be doing it there because the outline here sort of goes up and over here, and it goes down over here to some other part of the board, you know, some chips down here or whatever. So it's got to be that. It's got to freaking be that. I can't. How could the board that's had no rework done on it have 2 shorts like this? I mean, maybe there's more faults that I haven't even identified yet. I don't even know. So I think at this point, all we can really do is get that socket off there. And this time I'll record removing this and checking for that short, unlike what I did here where I cleared it before I had the cameras recording. I just had a thought, before I disturb anything on the board here, let's use the multimeter and see if we can see that short. So when I put the leads together, by the way, we're getting 0.58. So this is the socket right here. And this has got to be the data out pin because it's got the traces that go up and down. So I think this is the lowest it should be. Now it's moving around a little bit, but 0.85. And if we go here, it's a little bit higher. And we go to this one, and now we're in the 9s. And we go here, also 9 something. It's even higher over here. And it should keep going up. Yep, it keeps going up. So that means that the short is definitely right under here, and I predict it's literally right there, right under where this probe is. All right, I think the socket is out of there. Well, it looks like this half over here is definitely out because I can see it wobbling all the pins. This other side, on the other hand, nope, not out. Looks like one pin is still holding on. All right, and now it wobbles entirely. Let's see if I can get that out now. All right, it is out of the board. Where's the problem exactly? Because I don't see it. So I have the multimeter out, and the short is absolutely still there. And even with the eye loop, I don't see a problem. I don't see any issue here at all. Well, okay, so that was pretty disappointing. I was hoping I would have like a smoking gun and we'd have that thing fixed. There's obviously somewhere else on this board where that data line 7 is also on a similar chip or similar area of the board with the read-write signal, and they're getting combined somehow with a dead short as well. And I think at this point, I'm just gonna have to scour over the schematics here and just look for any chips that have both of those together. And then there might be a similar situation where the traces are too close to each other, because it's kind of unlikely that a chip itself could cause such a dead short like that, but I guess anything is possible. So I need to first find where on the board that chip might exist and see if we can figure out the problem. All right, I feel a little bit silly. I have the multimeter out here and I'm currently on the pins of the socket I just removed from the board. And we can see here, we're getting, if I push down really hard, you know, 0.88, kind of similar to what we have. Well, it goes without saying that these other RAM chips also have those 2 signals there. And look at this one, 0.8, 0.79. Let's go back to the one I just took the socket off of. Now it drops a little bit. I think it like charges up capacitors or whatever. 0.87. So this one is higher right here. Look at that, quite a bit higher. Well, lower, I mean. Yeah, we're down in the under 8. And then let's check the third chip here. This is the bank 3. Look, 0.89 as well. So the problem has to be under this chip right here. That's what I'm thinking. Because it goes down into the 0.7s. Oh, so I took that socket off for no reason. Okay. Let me remove this socket now. I can see the short circuit on here. I can see it. I have no idea if the camera is going to pick it up here. I'm going to tilt this up so it's a little more obvious. Let's turn the good old multimeter on and set it for beep mode. So from there to there, still shorted. But if I take the knife, there's just something there in this little groove. Let's see if it still shorts. I hope it doesn't. There it is. It's cleared. It's freaking cleared. I can't believe it. That was it. That was it. Oh, what's the deal with this motherboard? Seriously. I don't understand. It's like pretty nice quality with the gold plating and everything, and yet it has these issues. You know, I have to imagine that this worked at some point, and I can just fathom that someone like plugged a RAM chip in here and it killed it. Or they plugged a card into this expansion slot and that killed the motherboard, like it stopped working. Imagine how frustrating that would be. And you would like could change every single chip on here and that wouldn't even fix the problem. I guess that's kind of one of the problems with these clone things. That news report I showed a little bit of in the first video, if you go watch that, they talk about how there was like no warranty support for a lot of these illegal clones. And these kinds of issues are like, you know, things that can actually happen. I mean, look, it happened. We don't know how long this machine was in use for before this happened. Although, a few of the RAM chips that had been swapped out on here were from 1989. So that implies that someone was using it up until that point and then it broke. But I don't know. Maybe they changed those chips out to try to get this thing working. And of course, never would have worked with these shorts. Let me get a couple new sockets in here and maybe, just maybe, this thing will actually work. Oh. All right, so the 2 new sockets are in. I haven't reinstalled the expansion slot. Let's double check that it's not shorted anymore. Definitely on continuity mode. No short. Excellent. Let me just check for any other shorts of adjacent pins, because anytime you change a socket, I mean, that is always possible. Uh-oh, like right there seems to be a short. Let's double check to see what I did. I probably bridged a couple things while soldering. We got to look up what those pins are. So pins 11 and 12 are what are shorted together. And when we look here, 11 and 12 are address line 1 and 2. Those should not be shorted together. Now the question is, did I just cause that by putting these sockets on? I might have. And my assumption is those were not shorted before, like when running the diagnostic ROMs. This is definitely something that's happened after the fact. So I'm going to go try to figure out what's wrong. I'm going to use the same methodology with the multimeter and like the ohms mode. And my assumption is it's going to be under one of these 2 sockets. And I caused this problem. Well, that didn't take long. I didn't actually do anything. All I did was test again and the short's gone. So let's just check again. I'm going to go through all these pins in pairs. Yeah, short's gone. So there must have been just a little piece of solder blob or wire. That beep was me just touching the probes together, and just moving the board around caused it to come free. So there is no longer a short on the board. And I am noticing on the bench, there's like a bunch of little pieces of metal and stuff. So it's quite possible there was just something under the motherboard right there. Now, incidentally, I want to mention that I changed out these 2 sockets. I did clean up the flux, but I noticed that there's rework like right here. And a couple of these other sockets have been changed. This might be the only one that's obvious right here. And let's look at that socket. Ah, look, it's a green little socket there. It's that one. I'm also noticing that this board is filled with sockets like this, but it's also filled with sockets like this. See this one where the keyboard connector is? There's some of these under ICs as well. But it looks like those were probably installed originally, although that socket's definitely been swapped right there. And what kind of socket is that under this chip here? This looks like one of the regular sockets. So I'm wondering if this board's had rework for this exact same shorting problem. It is time for testing. I have a RAM chip back in that socket. I'm going to leave that one out. Everything else on the board should be good to go. I have these muxes back in here. These are the ones that connect the RAM to the CPU. I think we're ready to go. We're going to start with the diagnostic ROM. I'm not going to go right to AppleSoft. I have the speaker connected, the video connected. Let's power this on. Okay, excellent. Excellent start. Okay, lowercase, we're going to get to the inverse text. We're going to get to the flashing text. Is this going to work? Are the problems solved? Here we go. Yes, yes, it's working. Oh, okay, okay. I want to see the flashing text. I want to see the flashing text. I can't even believe this thing has been so much trouble. Flashing text, give it some flashing. No, it's seizure. There it is, flashing text. Okay. Wow. I am flipping down the switch. Are we going to get to AppleSoft Basic? There it is. It's the flashing product. It's working. I can't even believe it. It's fixed. It's actually fixed. Now, I know watching the video hasn't been that long, but the reality of me trying to find these shorts and stuff, yeah, there's a lot of hours in this. A lot of hours. These types of problems with the shorts are really, really hard to troubleshoot. And the thing is, with this board, you know, everything's in sockets. You could have taken every single chip out and put them in the Retro Chip Tester Pro here and tried to see if they were good, and they would have all been good. Now, some of the RAM I think is bad, but I guess we should, I don't know, reinstall it in the board and then see if that stuff tests good, because now we can boot a floppy disk. The thing is, every single chip on here, oh, except for the CPU, is original. It's all original. So in fact, I have the CPU right here. Let's switch back to that. I switched it out thinking it was bad, but I actually don't really know. It just was looking a little bit weird on the behavior, but it might be fine. And we're gonna find out momentarily here. And to be honest, if this CPU is fine, then every single chip on this board right now is original. And I'm gonna pop out the diagnostic card, we don't need it now. And let's turn it on. The CPU works. Every single chip on here is good, except for those 2 transistors. I'm gonna reinstall the RAM here, this other RAM that all tested good, and then I'll put in some of the chips that tested bad. In fact, I'm gonna put chips that tested bad in here, these Siemens chips right here, and then we'll see what happens. Okay, all 48K are repopulated. I used all the Siemens chips, including some of the ones that I had tested bad, and then I put a couple MOSTEC in here because there's a few missing. Let's see what happens if I turn this thing on. Okay, doesn't mean the chips are good or bad, but it means they're not crashing the bus. What I need to do now is I'm gonna get a disk controller and we're gonna boot up some diagnostics on this thing. Incidentally, I took each of these ROM chips that are on this board and I put them into the Retro Chip Tester Pro, and that thing is able to do a checksum and then tell me if the chip is known to be matched to something or if it's something that has a checksum that doesn't match anything. And this is what I found. The F8 ROM is an original Apple II, I guess, auto start ROM. Then we have 2 Franklin Ace ROMs, F0 and E8, and then E0 is this checksum here, which doesn't match anything in its database, so I did dump that. And then the D8 and the D0 are from the Apple II J Plus machine. That's weird. Alrighty, I have a disk drive right here and a regular Apple disk controller card plugged in. Let's turn this on. There's nothing on the disk drive, so that's unusual. Maybe this ROM doesn't auto start. I do have a tick mark on there to indicate that it works, but powering on we don't get anything. But maybe this weird combination of ROMs, you have to type PR number 6 to start the disk drive. So let me go grab the keyboard. All right, here's the keyboard, and I haven't taken this out, and it's a little rusty. I haven't really seen that, so I guess a bunch of water had been pouring on top of the computer, and maybe that's why the bottom was so rusty. But yeah, interesting how this works. It has an EEPROM there and some TTL logic. So I guess instead of an encoder, like a microcontroller on there, like the regular Apple keyboards have, it uses this. And look, it's got a switch right here, which I wouldn't be surprised if this turns on and off the lowercase encoding. So who knows if this thing supports shift key. So you turn that and then you push the H and you'll get a lowercase h. It's not ideal, but I think that's not an unusual way of doing it. Incidentally, if you recall, the pins were all bent up on this thing, and I went ahead and I fixed those. So I don't know how focused that is, but it's in pretty good shape now. What's not in super good shape is the socket on the motherboard, so I might have to swap that out, but I'm just going to try to slide this up. Just going to make sure there's no little metal shavings that could go underneath the motherboard. There are a few on the bench. Let's see if the keyboard works at all. Let me unplug the keyboard. Okay, so that's interesting. Why did it not work? Oh, I just realized maybe I had this plugged in wrong because there's no notch on the connector and no stripe on the cable. So let's hope I didn't damage anything plugging it in backwards, but I might have killed the keyboard. I don't even know. Yeah, that's not good. I don't have anything working on the keyboard here. Luckily, all the chips on here are TTL except for the EEPROM, which, you know, I don't know what's in there. So we could swap out those chips if there was some kind of damage. Now, I've had problems in the past with these little ribbon cable connectors, I think on the Apple II that I worked on, the original one. So I might need a new cable, but I think let's put some Deoxit in the keyboard socket here, see if that makes any difference. Okay, let's see. Nope, nothing. Nothing at all. Well, I'm probing around, and my assumption is that these TTL chips here and the ones on the keyboard, they're lined up in the same direction with the notch facing to the left. And if I go on to this pin here, we have continuity, and that's basically the 5-volt pin. But when I go to the ground pin, we don't have continuity. And looking at this connector here, which should match what's on the motherboard, this right here is ground, and this pin here is 5 volts, which does match. And when we plug in the cable, remember, the 5 volts on these chips here actually matches up to the 5 volts on the motherboard, but the ground, that does not. And if we look at this cable here, it should be this pin right here that goes to ground. Let's see. It does. So I think this socket is bad on the motherboard, and it might have come from me plugging stuff into it to reset the CPU. So I'm going to swap this socket, and hopefully that'll make this keyboard work. Okay, connector is swapped out. I used one of those like round hole type, so I had a nice firm connection there. It's connected up. Let's see if the TTL ground pin now makes its way to these chips. It does to that one. And the 5 volts? Yes. Okay, excellent. Let's turn on the power and see what happens. Oh, the disk is booting and the lights on the keyboard. Okay, reset works. So excellent. Let me just quickly see which keys are actually working. All right, does look like we have some problematic keys. So this is the list: S, the back arrow, period, slash, right shift, and the X key. Now, I'm not surprised about the back arrow, period, slash, or right shift, because that's where all that rust was on this keyboard here. See all this rust right here? So I'm not surprised that stuff is problematic. But the S and the X, that's on the other side of the board where there's rust over there too, to be honest. So who knows what's happened to this keyboard. Now, luckily, the key switches on this thing are Alps SKCC switches, which are rebuildable, and I think I have some spare parts and stuff like that. So I should be able to get this keyboard working. But what I want to do is boot up this floppy disk here, Apple Cylin, so we can run some RAM tests. Now, one thing is there is a reset key or button, and you don't have to push control or anything, so you could accidentally hit that. What about this toggle switch? Ah, okay, the toggle switch makes it where you have to push control and reset. Okay, that's much better. Now, the power button that's on this keyboard, let me see if I can put this in the view of the camera. This power button here, it is a button as well, but what does it do? It doesn't seem to do anything when you push it. What about these shortcuts? Oh yeah! So it types out the shortcut for you. So you can push that key and J and you get inverse, and now we have inverse text. Well, sort of inverse text. All right, well, let's boot the disk here. I'm using the shortcut. We'll hit enter, and let's test the RAM, because we put all that RAM in there. Oh, that's funny. The text is inverted even after booting this software here. So we're gonna test the RAM memory. Yes, random access memory. And we're gonna test the low stuff first. Ah, we gotta push the S key to start. I don't have an S key. What I do have, though, is sign parentheses as a shortcut key. What if we do that? Oh, it worked! So I pushed the power key and the plus on the number pad, and that was SIN with a parenthesis. So S was enough to get it started. So is this RAM test working? Yes, I think it's already looped around once. We already know the memory is working on this, the low memory. The computer wouldn't boot properly if it weren't for that, right? So we're good there. Let's reset out of this and let's run the high memory test, which is that upper memory here and we installed these Siemens chips, many of which tested bad on the Retro Chip Tester Pro. In fact, all of these ones here have an X on them. So I think these and one of these was a bad chip. Some of them tested good, but most of them tested bad. So we're going to test the high RAM, and I'm going to do my trick with the power button and the plus to start, and there it goes. And it looks fine. So that means this RAM is good, even though the Retro Chip Tester Pro said it was bad. So I think what's happening there is the TTL thresholds or the output drivers of this isn't quite compatible with the Retro Chip Tester Pro, which is a CMOS device, and that can cause false bad or negative readings. Okay, so it's already looped around once. So all the RAM is good on this thing. We have a good freaking working system. All right, what I would like to do now is boot up Fat City, which is a game that I kind of always run whenever I do these tests. Let's see if this works. I'm gonna have to power cycle the computer because there's no Control-Alt-Delete or Open Apple Control Reset on this. This is the ultimate test to see if this thing's gonna work. So far, so good. Come on, come on. The colors are way off. Oh, the colors are really bad. Okay, so, uh-oh. Uh-oh. So there we go. This machine still has faults. I mean, it didn't crash. Okay, so one of the things I'm noticing, let's power cycle that again. That title screen there should have had 6 colors on it. And we weren't seeing 6 colors. We were only seeing, well, black, white, and then the green and the pinkish color. So we're missing colors there, so that's a problem. But then this started going crazy, and I think this is the, it's switching pages between the high-res pages and stuff, and that's clearly not working. Yes, something's very wrong. It shouldn't be in the mixed mode there. We can type Adrian here, at least those keys are working. And that is obviously not working properly, and it looks like the game actually froze completely. Well, I think I'm gonna end this video here. This motherboard has put me through the ringer. I'm not sure I ever had something as difficult to fix as this, at least when it comes to those problems with those shorts. Those are bad problems to fix, and I've never run into a board ever that had shorts like that were not caused by some kind of rework that someone had done in the past, and they put too much solder or whatever, they lifted a trace and that caused a short. This thing had 2 of those that are some kind of manufacturing defects that must have been okay enough to make this thing work when it was new, and then it got worse over time. I really am curious to know if the previous owner of this thing had a working computer and then one day they plugged a card in there or changed a RAM chip and the thing stopped working because they bent the board slightly or whatever happened. And I mean, it is kind of funny actually in a way that currently as it sits, every single component that was originally on this thing from when it was made is still on this board and it's working. Except of course for the 2 transistors, well the 3 transistors, I changed the one that I didn't need to change, but I changed the other 2. And maybe that we have some bad RAM here that's causing the problems we saw in that game. I didn't even have to deoxit any of the sockets on this thing. They all worked, even though a lot of them are those terrible, crappy sockets. The only socket that stopped working is the keyboard socket, and I think that was my fault. I stuck a little wire in there so I could reboot the computer without power cycling it, and I think I damaged, it was like a cheap single wipe socket. So look for a part 3 where I troubleshoot this motherboard and I try to get it working 100% if it will allow me. It might just keep breaking, who knows. And then I need to try to fix this keyboard so I can get this thing back together, and it will be a little rough and tumble because the whole bottom plate is a mess too, but cosmetically, if you don't look at the bottom and you don't look at the keyboard, it's in really good shape. And this thing is a great example of an illegal Apple II clone that Apple didn't want you to have, but someone bought it and it got into my hands. So If you like this video, I'd appreciate a thumbs up. If you didn't, you know what to do. Definitely hit that subscribe button if you haven't already. Comment down below if you have thoughts about this whole thing. And I want to thank my patrons. Their names are scrolling up the side of the screen. They're rock stars. They keep me going and this channel going, which is absolutely amazing. I wouldn't be doing this if it weren't for them. So if you want to become a patron, you can do so with the link in the description below. And I guess that's going to be that. So stay healthy, stay safe, and I'll see you next time. Bye.